Hello everyone, thanks for being here. In this talk, I will share our journey to migrate our center's most critical software framework to GPUs. This is a joint work with many of my colleagues at BP and field collaborators from NVIDIA team. So in December last year, our center received our first production scale GPU cluster. So some of you may know BP HPC Center used to be a very big Intel shop. We have been buying various generations of Intel CPUs for over 2 decades. And last year was the first year we got a production scale GPU cluster. And we got this cluster from Lenovo. This cluster consists of 40 nodes, each with 8 H100 GPU card. So it's an 8-way GPU server. And the RPEAK of this GPU cluster is approximately 21 petaflops. And this cluster uses the direct-to-chip liquid cooling technology to maximize for the energy efficiency. So last year, our procurement was mainly constrained by power. We had a power budget of only 400 kilowatts, and these 21 petaflops is all we can get. But hopefully, in the near future, once we get more capacity, update our facility power, then we can get more machines to increase the compute capacity in our center. And we plan to use this GPU cluster to support a wide range of applications, including both traditional seismic imaging R&D, reservoir molecular simulations, as well as some emerging AI, ML, or even quantum projects. So there are 2 motivations for getting this GPU cluster. First is we want to increase the compute capacity in our center to support the ever-growing business needs, computing needs across different teams at BP. And now, given the GPUs are widely considered as the most energy efficient solution, we see the GPU clusters are leading the top 500 Green 500 rankings. And looking at our peers in the energy industry, most of them already completed the GPU transition. So we believe the GPU transition should be the right direction for us too to increase our center's compute capacity given the power constraint we're facing. And then the second motivation is really to upscale our teams in GPU programming and the ability to handle various HPC and AI projects on GPU cluster, hopefully to unlock some more capabilities for BP. Now, in order to justify the GPU cluster procurement, first we need to ensure our key applications can actually run on that GPU cluster. And second, we need to make sure that our applications can actually leverage the GPU cluster effectively by showing some economical advantage in addition to speed advantage. So with improved energy efficiency or performance per watt, or with improved cost effectiveness or performance per dollar. But first, we need to figure out what are the key applications running at our center. So we look at our cluster usage over the past 8 years, and we found the imaging applications are always using the most computing resources in our center. So at BP, our seismic imaging technology team seems to be able to saturate whatever computing resources made available to them. And previously, their workload was dominated by running acoustic RTM and acoustic FWI. And more recently, they started to develop and test a series of new applications, including elastic FWI, wave equation travel time Kirchhoff, and least square RTM. Those are all very expensive applications consuming lots of computing resources. And last year, our center got especially busy in order to accommodate these additional computing needs. So definitely, we need to migrate those key imaging applications to GPUs and demonstrate they can leverage the GPU cluster effectively. So for the rest of the talk, I will show you how we migrate those key imaging applications to GPUs and show some numbers to demonstrate the energy and cost advantage of moving this application from CPU cluster to GPU cluster. So first, a few things about our imaging application. So at BP, most of our key imaging applications were developed on top of a common framework, the seismic imaging software framework. This framework was developed entirely in-house for over 15 years by many generations of imaging researchers and HPC developers. It contains over 90,000 lines of code, optimized for Intel CPU only. So that's why our center has been so locked into Intel CPU for over 2 decades in order to support this code base. And to compile this framework, it takes over 20 minutes. All the makefiles are manually written. They don't support parallel build, so it's very outdated. And we have many, many input options for RTM and FWI, so lots of bells and whistles. Definitely need some careful planning if we want to move this framework to GPU. And this framework also heavily depends on 3D FFTs, 3D real to complex and complex to real in-place FFTs. So our researchers use these 3D FFTs to develop the acoustic wave propagators, which are the engines for our imaging applications. So far at BP, most of our production jobs are still acoustic, and we like to use the pseudospectral FFT-based propagators rather than the more commonly used finite difference wave propagators. But hopefully, we will see more elastic finite difference production jobs coming in later this year. And here in this table, I listed 3 commonly used pseudospectral-based wave propagators. PA-ISO is pseudo-analytical isotropic. BS-TTI is pseudospectral TTI, and FFT-TTI is Fourier finite difference TTI propagator. So for all those FFT pseudospectral-based propagators, over 70% of their runtime is spent in computing FFTs. And apart from the propagators, we also have researchers using 3D FFTs to develop angle-gather imaging condition. So FFTs are everywhere in our imaging framework, and it's dominating the performance of our imaging applications. And if we want to move this framework to GPU, we definitely need a very efficient GPU-based FFT engine. And another thing about our FFT usage in the legacy CPU code is all those FFTs are single-node FFT, so we don't do any domain decomposition because the communication pattern for distributed 3D FFT is all-to-all, so it's very heavy communication to cross-node. Whenever we want to cross-node, there is always a big performance dent. And in the past, we simply avoid doing that. So the code is simply not designed to incorporate any domain decomposition. But now if we want to move the code to GPU, GPU has much smaller memory, then we definitely need to do domain decomposition, which requires some structural change to the code. Not only we need to domain decompose the wave simulation, but many other peripheral components like the data injection, the imaging condition, etc. In addition, we also need the vendor to provide a very efficient distributed FFT library and fast interconnects between GPUs to support the heavy communication 3D distributed FFTs. And another challenge we're facing is at BP, we have very heavy ongoing research on FWI. So we don't just run a single FWI, we have a garden of FWIs. Each imaging researcher is writing his own FWI variants. But luckily, all those FWI variants were derived based on a common acoustic FWI code. So we could just focus on porting that acoustic FWI code to GPU first and make sure it's easy to modify, easy to extend, so that the other researchers can easily experiment their ideas on top of this GPU FWI code. To address those challenges, we made many decisions when building the software from the very early stage. So first, for the algorithm, we decided to stay with the FFT-based propagators rather than adopting the more commonly used finite difference wave propagators. So at BP, our researchers like the FFT-based propagators because they are able to generate much cleaner wavefield. And it's very easy to write the FFT-based propagators too. We just use the FFT API and rely on the vendor to optimize for the FFT computation to handle the communication between different processes. And our primary concern with the FFT-based propagator is its algorithm and its communication pattern may not fit for GPU architecture. So we may not see any speed advantage or any economical advantage by moving this FFT-based propagator from CPU to GPU. And internally at BP, we actually had many debates between finite difference route and FFT route. Every few months, people will bring this to the table. And the HPC team actually spent 1 year working along the finite difference route. So we write a finite difference-based RTM on GPU, but eventually we had to give up because it was very hard to QC against the existing FFT-based CPU code. Finite difference and FFT, they generate different wavefields. And when you see the difference in the final image results, it's very hard to track whether that difference comes from the numerical scheme for the wave simulation or from other components, some bug in the code. So it's very challenging. We had to give up, but focus on the FFT route instead. Then for software design, we decided to build the new GPU code from scratch rather than adding the GPU backends to the existing CPU code. Of course, we didn't try to replicate the 90,000 lines of code in Fortran. We cut many details. We were able to do that because many of those details only exist for papers. People don't use them anymore. And before we started writing our own GPU code, we actually work very closely with our users. So we look at our cluster usage and identify the top users for each imaging application. and talk to them to identify the key features, the key input options to minimize the porting workload. And we also try to preserve most of the CPU code structure, the abstraction, because our CPU code already had a very mature design. So this helps to minimize the GPU code ramp-up time for people already familiar with the CPU code base. Then finally, for programming model, we simply use CUDA. We didn't use any high-level parallel programming model or domain-specific library. So with CUDA, it's very easy to interface with NVIDIA's CUDA-based library, like the compression library, like the FFT library, and it also allows us to deeply optimize many customized operators for our imaging application. So before we started writing our own GPU code, NVIDIA actually shared their energy SDK repo, which I found is a very good reference for many efficient CUDA implementations for imaging-related operators. And once I finish reading their code, I know there is no challenge along this CUDA route. Then why not just go with it? And for hardware, we decided to target NVIDIA's 8-way GPU node. So we focus on the 8-way design rather than 4-way design or 2-way design, simply because the 8-way design can provide a lot more combined GPU memory so that we don't have to cross-node. Remember, there's always a big performance dent if we want to cross-node. So we simply try to avoid doing that by buying a big memory GPU node. And we pick NVIDIA because so far only NVIDIA provides a stable multi-GPU FFT support. And for AMD and Intel, by the time we talked to them during the supercomputing conference last year, they only provide single GPU FFT support. So they cannot handle FFT problem beyond a single GPU card, which is a very big drawback. And for AMD, recently, we checked their ROC FFT documentation. They say they are providing some experimental multi-GPU FFT support now. So we definitely would like to try on their GPUs once their multi-GPU FFT support is stable. Another reason we go for NVIDIA's 8-way GPU node is we found NVIDIA's architecture has more efficient interconnect layout to handle FFT problems of various sizes. So for big problem, we can simply use all the GPUs in the node and leverage NVLink and NVSwitch to provide high bandwidth to support the communication-heavy distributed 3D FFTs. And for smaller problems, we can also feed multiple shots into a compute node. The reason we want to do that is because in practice, we had to handle many shots, thousands of shots. And FFT performance scaling is always sublinear when adding more GPUs. So in order to reduce the overall processing time for a shot gather, it's better to minimize the number of GPUs used for a shot and run multiple shots concurrently on that 8-way GPU node. And here on the bottom left of the slide, I show a case to handle a medium-sized FFT problem using 2 GPUs per shot and 4 shots per node. With NVIDIA's architecture, all the interconnects are fully utilized due to its NVSwitch design. While for AMD's architecture, most of the interconnects are wasted. So each pair of GPU is only connected by one infinity fabric. And on the right, I also have a table to analyze the GPU to GPU bandwidths between NVIDIA and AMD's 8-way node layout when using different GPUs per shot. We can see when using 2 GPUs or 4 GPUs per shot, apparently NVIDIA's architecture can provide much higher inter-GPU bandwidth. So this makes NVIDIA more efficient in handling those medium-sized FFT problems. So that's another reason we favor NVIDIA's design, and maybe that's another area AMD can improve in the future. Then to address our FWI garden, so this time we implement all the FWI workflow in Python. So compared to Fortran, Python is generally believed to be much easier to write, much easier to modify, and have a much broader ecosystem we can interface with. And we can also do some parallelization using Python. So we use MPI for Pi to parallelize the shots over the compute nodes, and we use Numba to parallelize some gradient smoothing operator on the FWI workflow. And now for the compute backend, the RTM operator and all the underlying modules are implemented in C++ and CUDA on GPU and interface with NVIDIA's library. So our RTM operator can function both as a forward modeling operator to compute for step lengths and also a real RTM operator to compute for gradient. we use Python 11 Seismic to generate the Python binding for this RTM operator. So basically, we separated the compute engines from the workflow. The compute engines are done in C++ and CUDA on GPU to optimize for speed and memory. And the workflow is done on the CPU side to optimize for researcher productivity. Now, if an FWI developer wants to do 4D FWI or probabilistic FWI or some other ML type of work on FWI, they can do it in Python. And if they want to write an efficient elastic propagator or some other imaging condition, they can do it in C++ and CUDA. So hopefully this new FWI design can help to accelerate both production and research FWI projects in the future. Now regarding to a timeline, we have been looking into the GPU direction for quite a few years. Like I said, first we follow everyone else to go along with the find a difference direction and quickly realize we will never going to get our project finished. So we quickly switched to the pseudospectral FFT route. We started by porting the pseudospectral isotropic and TTI propagators to GPU. We wrote a little propagator benchmark, a proxy app, and have them benchmark on NVIDIA's DGX A100 box. We then identify the speed advantage of using the 8-way GPU box to handle the FFT-based propagators. And then we spent 1 year writing RTM and most of the components for the imaging framework on GPU. And at the same time, our sysadmin team had a collaboration with Azure to set up Slurm on Cycle Cloud and also enabled access to many A100 instances on Azure. So at that time, we were asked by the upper management to evaluate the feasibility and cost of going to cloud to use GPUs. So once I finished writing the RTM code, we did a test on cloud. It was a production scale, high frequency RTM test. We burned a lot of money, but we were able to prove 3 things. So number 1, the GPU code works. It was able to replicate the CPU code results even for very big scale testing. And number 2, we finally demonstrated the energy advantage of the GPU solution. We showed a single A100 GPU card is about 4 times faster and 8 times more energy efficient than the in-house CPU node. And number 3, we look at the cost of running the GPU code on cloud, the compute cost and storage cost compared to the cost of running the CPU solution in-house. We found the in-house, the on-prem solution is much cheaper. So that means if we want to use the GPU code, we better get our own in-house GPU cluster. So late 2023, we made a procurement proposal to the upper management, and we started talking to various chip vendors to benchmark our propagator speeds, including NVIDIA's H100 GPU card. So this is the only GPU type NVIDIA guaranteed to deliver at that time. We couldn't get H200 or Blackwell. And we also did RFI, RFP to configure the compute nodes and get some pricing information. We then identified the cost advantage of the 8-way GPU node. So earlier last year, we finally got the budget approval and placed the order, but we had to wait for a whole year for the cluster to arrive due to some stocking issue on NVIDIA and Lenovo's side. And during this waiting period, we keep using the A100 instances we had access to on Azure to test our GPU code. And we also keep working with NVIDIA team to optimize our FFD TTI propagator, the propagator we use for FWI. And then later last year, we eventually launched the GPU acoustic FWI code. And later last year, we also set up a series of CUDA training workshops with the help of NVIDIA team to upscale our team in GPU in CUDA programming. So before I show the numbers to demonstrate the energy and the cost advantage of the GPU solution, let's first look at some machine specifications. So we try to compare the H100 GPU node against 2 of our in-house Intel CPU nodes, Cascade Lake AP and Sapphire Rapids. On our Sapphire Rapids node, we have some HBM on it. And on the GPU node, apart from the 2 terabyte CPU memory, 8 by 80 gigabytes GPU memory, this time we also equip the GPU node with lots of disk storage. So on the GPU side, each GPU is paired with a 3.2 terabytes NVMe SSD to enable GPU direct storage, which can be used to keep the wayfile snapshots for RTM. And on the CPU side, we also have about additional 50 terabytes NVMe drives which can be used to keep the distributed input data for FWI, and then we can reuse them for every inversion iterations without having to create further traffic to Lustre. And from looking at this table, we can also get how much our peak improvement, the performance improvement, and energy efficiency improvement we should expect for this H100 GPU node. But remember, these are just paper numbers. In practice, most of our imaging applications are memory bandwidth bound rather than compute bound. So we need to collect the data ourselves. So first, let's look at the PSTTI speed propagator benchmarking results. So PSTTI is a FFT-based propagator which we widely used for our production RTM jobs. And this is also the propagator benchmark we send to various chip vendors for architecture evaluation. And like I said, 70% of the runtime in PSTTI is spent in computing FFTs. So benchmarking PSTTI is essentially benchmarking the 3D FFT performance. And the pattern we see for PSTTI here also reflects the pattern for other FFT-based propagators. So here on the top, I plot the PSTTI speeds for various problem sizes ranging from 500 to over 2,000. These problem sizes are mixed radix numbers. So in our imaging code, the simulation domain is always padded to these mixed radix numbers to optimize for FFT performance. And different line here represents the speeds using different number of GPUs, with the right line on the top using a GPU, and the deep blue line on the bottom using only one GPU. We see the speeds are changing, are fluctuating for different sizes. So that's why we need to collect all of them rather than looking at a particular size, which might give us some misleading conclusion. And for smaller problems, we see the speeds using a GPU, the right line is actually lower than the speeds using 4 GPU or 2 GPU. So that's why we keep telling our users when using this 8-way GPU node, for smaller problems, better fit multiple shots into the compute node to maximize the resource usage. And then on the bottom, we show the scale speeds. So basically, we scale the speeds below, we scale the speeds above by how many shots we can fit into a GPU node to derive the overall performance on that 8-way GPU node given the shot configuration, how many GPUs we use for a shot. And we see for each problem size, using the least number of GPUs for a shot always gives us the best overall performance on that 8-way GPU node, which indicates the sublinear behavior of the FFT performance. And it also tells us in order to reduce the overall processing time for a shot gather, better minimize the number of GPUs used for a shot and run multiple shots concurrently on that 8-way GPU node. Now let's compare the GPU nodes against two of our in-house Intel CPU nodes. So on all three machines, we compare their optimal speeds for each problem size. And by optimal speeds, I mean we pick the highest value of all the scale speeds using different GPU configuration on the GPU node or different thread configuration on the CPU node. And we can see on average, the H100 GPU node is about 41 times faster than Cascade Lake and 28 times faster than Sapphire Rapids. Now, in terms of energy efficiency, H100 GPU node consumes only 8 times more power than these Intel CPU nodes. So in terms of performance per watt, H100 wins. And for cost effectiveness, H100 GPU node is no more than 17 times the cost of these two Intel CPU nodes. So in terms of performance per dollar, H100 also wins. So this comparison helps to justify the procurement of this GPU cluster. And another thing I want to mention here is all these runtime speedups are actually lower bounds because in practice, sometimes we simply cannot fit multiple shots into a CPU node because the CPU node has much smaller disk storage. So sometimes it doesn't have enough space to hold the wave snapshots generated from multiple shots. So in practice, we should see even higher runtime speedups, and that translates to even better energy efficiency and cost effectiveness. Now, let's see some numbers for the production jobs. The first test we did is a 35 Hz acoustic TTI RTM test. The input shot gather contains over 3,000 shots, and we use the PSTTI propagator. And here I show the image results generated by the CPU code, by the GPU code, the difference, and the relative error map. All the image results, they are plotted using the same color bar range. And for the relative error map, red color is only 5%, and blue color is 0%. And most of the relative errors are blue, so they are close to the 0%. That means the GPU solution is very, very close to the CPU solution. We can't make them 100% fully aligned due to some floating point precision or calculation order differences between CPU code and the GPU code. But our researcher cannot spot any difference by eyes, so this minor difference shouldn't affect their interpretation. Now let's move to the performance benchmarking results. So we have 3 tests here. They all use the same number of CPU nodes and GPU cards. So we try to compare one CPU node against one GPU card, and we also submitted the same number of jobs. Each job will run on only one CPU node or one GPU card, and they will handle 11 shots one by one. Now for the runtime results, we see a single H100 GPU card is about 9 times faster than Cascade Lake and 7 times faster than Sapphire Rapids. And if we multiply this speed up number by 8, we can get the runtime speed up for using the 8-way H100 GPU node. And for total energy consumption, the GPU solution is able to reduce it by 8 to almost 10 times. That amounts to about $2,000 saving in our electricity bill. And for memory footprint, we see the GPU memory usage for the GPU test case is much lower than the CPU memory usage for the CPU test case. That's because we optimize both speed and memory. We only keep what's necessary for time stepping into the GPU memory. Now moving on to FWI, we did a 30 Hz acoustic TTI FWI test using GOM data. And here we use the FFT TTI propagator, which is about 3 times faster than PSTTI propagator because it contains fewer number of FFTs. And this is also a highly optimized propagator for Hopper. We had NVIDIA team helping us to optimize the finite difference components of this FFT TTI propagator. So we should expect even higher runtime speed up than the previous PSTTI-based RTM test. And again, here I show some velocity results and gradient results of the final inversion iteration of the FWI test just to demonstrate our GPU code is able to replicate the CPU code results. Moving to performance results, again, we use the same number of CPU nodes and GPU card, try to compare one CPU node against one GPU card. And now here for the runtime, we see the runtime speed up is actually lower than the previous PSTI-based RTM. That's because currently on our GPU node, we have only exposed the CPU side local storage. The GPU side local storage for GPU direct storage is not completely configured yet. So right now, the GPU node doesn't have sufficient disk I/O bandwidth to hide the wavefield track pointing. As now we are using the FFT TTI propagator 3 times faster than PSTTI propagator, so the wave simulation time is shorter. It no longer hides the wavefield track pointing to the local drives. As a result, the GPUs are turning idle alternatively to compete for the disk I/O bandwidth. And currently, our sysadmin team is working hard to bring this GPU side local storage online. Once this is done, we will get much higher disk I/O bandwidth. And then hopefully this GPU stalling issue will disappear. But that's not a big problem because right now we already have some solution on the software side to overcome this limited disk I/O bandwidth problem. We use NVIDIA's floating point compression library to compress the wavefield before sending them from GPU to the local storage. And here I show the results of the FWI test with wavefield compression. And we see the GPU solution remains very, very close to the CPU solution, which means our wavefield compression setup is actually quite effective. And for performance benchmarking results, we see with wavefield compression, now we get much better runtime speed up and energy reduction. As a result, the 8-way H100 GPU node is about 88 times faster than Cascade Lake and 52 times faster than Sapphire Rapids. So to conclude this talk, we completed migrating our acoustic RTM FWI application and most components of the imaging framework to GPUs. This GPU migration project helped to influence our decision between go to cloud versus stay on-prem, and also help to influence BP's first production scale GPU cluster procurement and selection. The resulting GPU solution features a modernized software design and also delivers compelling runtime speedups, energy and cost advantage, which help to justify the procurement of this GPU cluster and also help to reduce the in-house project cycles and lower the operating costs. So hopefully this new GPU cluster, together with the code we have developed over the years and people we have trained, will help BP to unlock more capabilities, especially for seismic imaging. So for future directions, since last year, we have already been working with NVIDIA team to port some of our elastic FWI propagator to GPU. And this year, we plan to get more elastic FWI propagators ported to GPU and push some elastic FWI code to production. And we also plan to add the compute backends to support other accelerators for performance portability. So here is the list of paper references published by my colleagues about this code base. If you're interested, you can take a read. And with that, I'm happy to take any questions. Thank you for your attention.
Thank you, Muhong. Do we have any questions? Again, up front, I'll bring you a mic for recording. If you're in the back, speak up loudly.
Thank you for your presentation. So you mentioned about the compression. So what compression method you've been using for your?
NVIDIA's NVCom compression, floating point compression library.
It's in-house. Oh, sorry. It's
NVIDIA's proprietary library. Compression library.
Okay.
Speak up. Here.
Thanks. I saw even with compression that there was a lot more storage load for GPU. Is that just because staging multiple shots?
Which are you talking about?
Yeah, even this one, like 4 times the local storage footprint. Is that just because you're staging multiple shots for the GPUs?
No. This is per node, not per GPU. So one node has 8 GPU, and we put 8 shots into this 8-way GPU node. So that's why it's much higher than the CPU side local storage.